All right, welcome to Methods of Enumeration. But before I get into that, I want you to notice when we were doing Venn diagrams, we were doing the raw count or the probability. I want you to notice that there's one very natural way to describe this situation. It's a situation where two characteristics, call it characteristic A and not characteristic A, characteristic B and not characteristic B, come into play. So some of the problems might describe in words that consider people that own dogs. Well, then there are people that don't own dogs. That might be one set A. And then maybe we have people that like beer, set B. Now we have people that own dogs and beer, or other descriptions. Those are an important quantification of this picture. This is generally a two characteristic picture. If we're dealing with three characteristics, it's getting much harder because notice you put an X, Y, Z, and Q here. There's only four variables. But when you do this, then you got X, Y, Z, P, Q, R, S, and T, and a number of variables are blowing up on you. To do a problem that contains three characteristics, and they're nots and ands and stuff, is much harder than a two characteristic problem. So I'm going to look at a two characteristic problem here, but I'm going to look at it in terms of enumeration. So initially, the first characteristic I'm going to look at is order versus unordered. So that's characteristic A, not characteristic A. So first off, let's imagine that we have a set of things. Typically, we start with a set A, and it has n things in it. So let's look at our class. We have 32 students. So the order of my set of students is 32. Now, let's do something with those students. Let's pick a king and queen of our class. So we're going to pick a king and queen. Now, obviously, if we want to call someone the king and someone the queen, or we can be politically more correct, president, vice president, or premier and vice premier, whatever you like, it seems that there's order in here. However, there also appears to be something else in this set, and that is, besides order, we can't let a person be a king and a queen and president and vice president. So there's another characteristic sitting in the background here, and that is with replacement or without replacement. So if you think of this example, it seems that this example looks like this. If we're going to pick two people from our class with order, because one's going to be called king and one's going to be called queen, we don't want the king to also be the queen, so we're going to do it ordered without replacement. Looks how many combinations we can do. This, 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 this. Looks like we have at least four ways to count things very simply with just those two characterizations. We add more things to it and it gets more complicated. So let's do this problem. Here's a simple way of thinking, and it's called the multiplication rule. When I have choices, like let's make a sandwich, and first we have 3 breads and 4 jams, sweet tooth today, that's it. Well, white, pumpernickel, and 9 grain, and then raspberry, orange, strawberry, and grape, let's say. Well, how many different sandwiches you can make? We're not going to add any more characteristics, no toasting, no cut or anything like that. We would just simply multiply 3 times 4 and say there's 12 possibilities. That's actually happens because of a tree. You start with the initial position, and then you go, bread 1, bread 2, bread 3. Once you've gone down one path, then you pick jam 1, jam 2, jam 3, jam 4, or jam 1, jam 2, jam 3, jam 4, or one last time, So how many paths are there to follow after 2 steps? Well, I have to just count across. There's 12. Multiplication rule. Now, let's say there's something like you can never put strawberry on pumpernickel. Well, these choices have a property of called independent. There are tons of vocabulary we're going to have to go through, and as each problem runs into new vocabulary, I will point it out. Right now, these are referred to as independent choices. So let's see if this works. Let's take our class of n people. So P1, P2, all the way to Pn. So we have, first we're going to pick the king. So we got these people. Now, how many subsequent choices do you have? Well, since we don't let this person be replaced because we're doing it without replacement, that person can't be the next one. If you pick P1, your choices are P2 up to Pn. If you pick 2, it's P1, skip to P2, P3 up to Pn. Now, I'm not going to draw out this whole tree. Instead, I'm going to use the same counting idea, but this time it's not independent choices, but there's a commonality. First, you had n choices, and your subsequent choice in every situation, every branch of this tree is n minus 1, n minus 1, n minus 1. It's just not the other person you picked. And so here is an enumeration of n people, pick 2 in order. Wow. It seems that I just gave a good vocalization of how we might write that. N people, pick 2 of them. Huh. What do you think n pick 3 would look like? Let's take a guess. Could it possibly be this? Go down again. Pick king, queen, and joker. President, vice president, treasurer. And you can see that this happens very quickly. Now, what would n pick k then be? Well, notice we're counting from 0 up to 2, that's a count of 3. From 0 up to 1, that's a count of 2. So it seems that from 0 up to 2 is 3, 0 up to k minus 1 is k. Looks like that's the formula. Now, this is not a very pleasant formula to write in this fashion, simply because it's got ... in it. Nobody likes ... That means you're supposed to recognize a pattern. Well, 2 people might recognize different patterns from the same thing. In fact, that's a great argument in science. One person sees one thing and it's a pattern, and someone else sees something else, and they can't agree, even though they're looking at the same thing. So I'm going to write down a formula that's less ambiguous than this, more direct. But in order to do that, I have to introduce you to the factorial symbol. So the symbol n with an exclamation point, and by the way, if you go on YouTube and look up some high school video, at some point you have a kid going to be reading in a high school class, and he's going to get to this and he's going to go, n! And he doesn't know that we call this n factorial. It's fun to laugh about that, but can you imagine that poor kid? God, he might be 45 years old now, and still everybody is watching him read an old 8mm tape, screaming out n because he didn't know what n factorial was. By definition, it means start at n, then multiply next down, and continue until you reach 1. So 5 factorial, 5 times 4 times 3 times 2 times 1, 20 times 6, why that's 120. 4 factorial is just 4 times 3 times 2 times 1, that's 12 times 2 is 24. Now, there's one oddball to this one. 1 factorial is not the oddball, starts at 1, ends at 1. It's 0 factorial. We notice it doesn't fit in this problem. Start at 0 and go up to 1, not the next one down. We just decide that we're going to define, and when I put a dot on the equals, When I put a dot on the equals, that means definition. We're going to define it to be the number 1. It turns out it's very useful mathematically to have this definition. Now, by a stroke of coincidence, this formula is almost a factorial. It's just missing what's after it. And I'm going to show you how we can write this. So here we go. How can we write n choose k, n pick k? Well, I'm going to start with n factorial. That'll give me n times n minus 1 times n minus 2, all the way down to 1. But I want to get n times n minus 1 times n minus 2 and count all the way to n minus k minus 1. I want to count 1 short of k, multiplications. Well, the only way to do that is to cancel out what I didn't get here. So over here, like 5 pick 3 really means 5 times 4 times 3, which really means 5 times 4 times 3, and that is indeed 5 pick 3. So it seems that it looks like this. It seems that this has just got something extra in the bottom. But is it n minus k factorial, or is it k factorial? Let's do another one, see what it says. Let's do 7 pick 2. 7 times 6, which is the same as 7 times 6 times 5 times 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. And it looks like we do 7 minus 2 to get the 5 factorial. And that produces that. So it looks like we need that rule. So there's a nice formula for our n choose, n pick k. I apologize, it twisted while I was talking. You're getting too little of the sheet here. All right, so we have with n pick k an ordered choice without replacement. Well, what happens if I replace them? Let's see if the tree tells us something. Person 1, person 2, up to person n, and we let them be replaced, and we get person 1 up to person n, person 1 up to person n. Well, oh my goodness, it looks like I have n choices followed by n choices. So if we do an ordered choice with replacement, it looks like we just get n times n, or n squared. And if we choose 3, n times n times n, n cubed. So it looks like we're getting n to the k, where the size of the set we're picking from is n things, and we're making k choices, ordered with replacement. Oh, our counting's not been so terrible. Looks like we have some nice formulas for you to memorize. One uses these factorials, one uses powers. Doesn't seem like it's terribly hard. Don't worry, any good mathematician can make a problem harder. So now, I'm going to actually do an example of picking 2 people, but then removing the order from them. Now, why am I going to pick them with order and remove the order? It turns out it's a very good way to count. It's an easier way to get to something. Order it, but then unorder it. It's weird. It's easier than counting the unordered choices. So here I'm going to go. I'm going to have 5 people, A, B, C, D, E. And I'm going to pick any 2 of them with order. Well, I know that power, that number, really easy. That is 5 pick 2, which is 5 factorial, or 3 factorial, which is 5, 4, 3, 2, 1 over 3, 2, 1. 5 minus 3, 2, 1. Cancel, cancel. I wrote the wrong formula. I apologize. I was getting the wrong answer. 5 factorial over 5 minus 3 factorial is 5 times 4 times 3 times 2 times 1 over 2 times 1. And that gives us, oops, 5 minus 2 is 3. And that gives us the 5 times 4. That means there's 20 ways to pick 2 from these 5 people. Now I could write them down. AB, AC, AD, AE, BA, BC, BD, BE. And I'm doing it without replacement. Well, you can see the pattern I was using. A first, others. B first, others. C first, other. D first, others. It's going to be easy to get 20, 5 rows of 4 and get 20. But now I'm going to unorder it. When there's an A first and a B second, that means also later there's a B first and an A second. When there's A first and a C second, that means later there's going to be a C first and an A second. They are paired. Every time we have a symbol star followed by a triangle, a square, later there'll be a square followed by a star. The ordered count is twice the size of what I want. So if I want to count the unordered pick of 2, which would be like a class committee. We're going to have a class committee of 2 to keep track of Dr. Sorensen. And there's not a president and vice president. There's not a king and queen. There's just 2 of you in a group. Well, that's 5, but we don't call it pick 2. We call it choosing 2 because the choice is without replacement, but it's unordered. So now we're going to do the unordered without replacement formula. We call it N choose K. And what it is the ordered choice, and then we divide it by the how many orders exist on K elements. And that order that exists on K elements without repeat is K factorial. Why is that? That's because it's K pick K, which is K factorial, 0 factorial, and all of a sudden we see like 0 factorial, we want it to be 1. That's how we found out the number of ordered things of size K. The number of ordered things of size 2, 2. Ordered things of size 3, 6. A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, C, B, A. Ordered, without replacement, picking everything in the set. K factorial. Kind of a special case of the N pick K. Well, this then produces the unique formula N factorial over N minus K factorial, K factorial. And by the way, you've probably seen this number before. People call it the binomial coefficient. So I'm going to demonstrate that this number has been seen. The 0th row, the first row, the second row, the third row. These are the combinatoric numbers, the N choose K. And you can check it. There's a symmetry to this. And so 0th, first, second, third, fourth. The rest are all f's, right? Why are these two weird? 0th. Oh, and this one, erd, but the rest are th. I'd like to know that. Some, linguists should tell me that. So anyway, let's do some of them. Let's do this one. See if we can use what we've learned, but realize it's a little bit more complicated than the straightforward formula. I would like my class of n students, let's set it equal to 7, and I'd like to do a picture of 4 in the front, 4 in the back, 3 in the front. How many ways can those people line up and I snap a picture of them? Now, if we think about this for a second, it's kind of an odd thing that we have to do. We have to divide them up and order them. And so what's the right way to count this? Well, one of the easiest ways to view this and to understand how it occurred is you might say, all right, I'm going to pick the people in the back row. Well, how many people do you have to pick from? 7. How many you put in the back row? 4. What is this? This is an ordered without replacement choice. So you've just got all of the people in the back row. Now, what's left is you have a set of 3 that you literally have to just get in order in the front, which is 3 pick 3, but it's also just 3 factorial. So here is that count. Now, it looks pretty simple, but every once in a while some odd things happen. And the odd things that happen is you sometimes inadvertently introduce order when you didn't mean to, or you inadvertently removed order when you wanted to keep it there. And we're going to look for signs of that, the characteristic of inadvertent mistakes. But right now, this is a wonderful calculation. And it shows how we use probabilities, multiplication rule of choices. Things are going nice. Now, there's some other weird things that we can do. Let's put a bunch of plates on a table. I'm going to put 6 plates on a table. And I'd like to put 3 coins that I have in 3 different bowls. No double. How many ways can I put my 3 coins in those 6 spots? 3 coins placed among 6 bowls. Well, what's going on here? Well, once we pick a bowl to put a coin in, it's not used again. So it has the characteristic of without replacement. But do we really care if the coins are identical, what order they get placed in? There's nickel, nickel, nickel? Or is it just these 3 have a nickel? Seems to me when I'm placing identical things, I cannot perceive the order in which they were placed if I close my eyes and open my eyes and see it. So what's happening is some objects have the characteristic of being indistinguishable. And applying the word indistinguishable is a tricky way of saying unordered. So if I want to place 3 identical coins, indistinguishable, among 6 bowls here, then I have to do 6 choose 3. Choose the 3 bowls, unordered, and then I go click, 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 drop the coins in. That's the answer to this question. So one has to be careful at understanding when you find order and unorder by how we say it. And because we're a language, English, Korean, Japanese, you pick it, we got tons of ways to say the same thing, and it can be very unnerving to read 3 questions in a row, all sound different, and they're exactly the same problem. So now, what have we done? We've done a couple of different ordered, without replacement, ordered with replacement, etc. Let's do a probability with this enumeration. So here we go, probability with enumeration. Well, one of the favorite things that mathematicians love to do is introduce a deck of cards. Now, I don't want to pick on somebody because they don't know about a deck of cards, or somebody's an expert at poker. Doesn't matter. We work with a deck in this class frequently, and a deck has 52 cards comprised of 4 suits, which are typically hearts, spades, diamonds, and clubs. And it's typical that hearts and diamonds are red, and that spades and clubs are black. And it also is the case that in a suit, we have ace, 2, 3, 4, all the way up to 10. And the next card we call jack, queen, king. But I want you to notice it's just 13 symbols, okay? Ace to king. 4 suits, 13 symbols, 4 times 13, 52. And we also induce red and black. And we also call these face cards. Some people include aces in the faces. So we'll make it clear when we say things like that. Here's a common thing. I'm going to deal you 2 cards. Sorry, 2 cards. So when we deal, this means something is randomly happening, but it's being done without replacement because 1 card goes out, there's 52 left. So let's begin with how many ways can I deal 2 cards? One very nice definition of probability for equitably likable, equitably, saying something wrong there. But I'm going to continue. So the number of all ways and the number of your ways is a probability. So let's deal 2 cards and ask what the probability of a pair is. Well, in order to do that probability, the number of all ways to deal 2 cards, pretty straightforward. They are unordered because when you get them in your hand, you just move them around anyway. You don't care the order that you come in. You just care what you have. So 52, choose 2, is unordered without replacement. So 52, choose 2. By the way, besides using binomial notation, binomial 52, choose 2, people also write it this way, 52, choose 2. Parentheses around 2 stacked numbers. It looks like a vector, and it's actually a calculation. Now, what are the number of your ways, the thing that you want to count? Well, how many pairs are there? Can we count them easily? If I have an ace, let's write down 4 aces. Ace heart, ace heart, ace, let me write, ace heart, ace club, ace diamond, ace spade. A pair is 4, choose 2. So there are 4 choose 2 pairs of aces. There are 4 choose 2 pairs of 2s. There are 4 choose 2 pairs of 3s. So using the multiplication rule, 4 choose 2, the number of pairs of a given number times your 13 numbers by the multiplication rule. Here is a probability of getting a pair given a deal of just 2 cards. Number of ways something happens, your ways, over the number of all ways. That's a good calculation. Equal likelihood events. There's the word I was looking for. All right, now we can mess with you a lot on these questions. Not because it's good to mess with students, it's just in reality there's lots of ways things show up. So here's the last enumeration question I'm going to do. I'm going to take a picture again, but this time I'm going to go up on the ceiling like in a hover thing, and I'm going to have each of you stand here and you're going to look up and smile at me. And have you stand in a circle. Now when I get that picture, even though it's on a frame, if I put it in a round frame, I can rotate this picture any way I like and it's still the same picture. It just has lack of orientation. What does that do to the count? Well, what I've done is a picture that looks like this. John Jim, Jerry, and Justin, when I wrap it into a picture, it's John, Jim, Jerry, and Justin, that's the same as what used to be the Jim, Jerry, Justin, John ordering. And it's the same as the Jerry, Justin, John, Jim ordering. And it's the same as the John, Jim, Jerry, Justin ordering. In other words, I have taken the four ordered ones that were possible, and they're all equal now. So I have removed four groups of people four lists become one picture. Four lists become one picture. Every time we have four people, it becomes a picture. So whatever number of people we're going to put in a circle, then I have to divide by that to remove the rotational ordering that I don't want. So let's do an example. Let's put 5 people in a circle pick. Well, how many orders of 5 people in a line are there? Well, 5 factorial. 5 pick 5. And then I have to divide by the 5 rotations. Why, the answer is 4 factorial. A different sort of count. But again, it had a count that then somehow removed an ordering that was necessary to be done in the problem. All right. I'm going to shoot up this YouTube link, and then I have to pick some good problems for you.